Hey, welcome back to Calculus. In this section, we're going to be looking at limits at infinity, section 2.6 from the text. So up until now, all of our limits that we've been considering, the input variable has been approaching a finite number on the axis, a number called a, and now we're going to let that input variable approach either plus or minus infinity and ask the same question. So you can see the objectives there. I want to tell you what the intuitive definition of a limit at infinity is. I want to relate it to a notion probably familiar to you from pre-calculus, horizontal asymptotes. I want to be able to compute the limit of infinity of any rational function, that is any ratio of two polynomials. And then I want to look at some special cases about exponential functions and the inverse tangent function, some facts that I just want you to know. Okay, so you can check out the definition here. It's taken from your book in section 2.6. What do I mean by a limit at infinity? I mean the same thing that I do for limits at numbers, that the output of a function is getting closer and closer to some value called L, but instead of letting x approach some number on the axis, I'm going to let x grow without bound. So I'm going to let x go to infinity. So I'll read this. The limit as x goes to infinity of f of x is L, and what I mean is that the outputs of the function can be made arbitrarily close to the number L by taking x to be larger and larger, growing without bound. All right, let's look at an example. Got a graph of a function drawn here, a rational function, y equals x squared minus 1 over x squared plus 1. It's drawn in blue. And you can see that as you look out, as x gets bigger and bigger and bigger, further and further right in the picture, that is, as x goes to infinity, or if you look to the left, further and further to the left, x goes to negative infinity, the y coordinates on that blue curve are getting closer and closer to the y coordinate y equals 1. Okay, so I'm going to write that down by saying the limit as x goes to infinity of that function is equal to 1. The limit as x goes to minus infinity of that function is also equal to 1. Okay, that's reading the picture to the left. And we will call the equation y equals 1. That's the equation of the horizontal asymptote. All right, so whenever a function has a limit at either infinity or minus infinity, then the value of that limit is the y value of the horizontal asymptote. The equation of the asymptote will be y equals that value. All right, so I did all of this with a graph, and you can always look at limits with graphs. So why not? You're never in a position where you can't say what a limit is if you can look at a picture of it. But it's a reasonable question, like, well, how could I calculate that limit using limit laws? So that's what I'm going to propose next. Is we're going to take a look at this theorem from your book. The preamble in this theorem about r being a rational number and things being defined, it just means that we're taking powers. You can't take square roots and so on of negative numbers. So I'm going to kind of gloss over all those details and just say that these expressions are defined. So what am I looking at? I'm looking at 1 over x to the something, and the something is a positive number. All right. And what this theorem is saying is that, well, because those denominators, x to the r itself, are going to grow without bound, either going to positive infinity or negative infinity, that the ratio of 1 over them will be 0. And in fact, you can take any constant. If you fix any constant c, something that doesn't depend on x, any number up there, and you divide it by something that's getting bigger and bigger, then the result is going to be 0. That's because big denominators make ratios want to be small. All right, so this is kind of a fundamental fact when you're thinking about ratios, or sorry, horizontal asymptotes or limits at infinity of rational functions. Let me show you why. Let's go back to our first example, our x squared minus 1 over x squared plus 1. We try to leave that theorem in view as we do this. So what am I going to do? Given a rational function, I identify the terms in it that have the highest powers of x, the highest degree. In this particular rational function, there are 2 such terms. One's in the numerator and one's in the denominator. That degree is x squared. So I divide everything, in this case, all 4 terms, by that highest power. I divide every one of the terms by the highest power of x, and then use rules of exponents to simplify them, right? So for example, if you're looking right here at this x squared over x squared, well, that certainly simplifies to 1. 1 over x squared is simplified. X squared over x squared is 1. 1 over x squared is simplified. So I simplify all 4 of those terms. And now how does this theorem 5, come into play? Well, any of these terms where there are still x's in the denominator, things didn't cancel. We're only going to have x's in the denominator because we divided by the highest power of x. So either the x's are going to cancel perfectly, like in the x squared over x squared, or they're going to leave some downstairs. And when you're left with x's downstairs, as x goes to infinity, those terms are going to go to 0. That's what theorem 5 is telling you. So if we simplify this thing a little bit further, that limit is going to be equal to, well, 1 minus 0 over 1 plus 0, and that's 1 over 1, and that's 1. So there's an algebraic computation of that same fact that we saw in the graph. And theorem 5 is valid as x goes to positive or minus or negative infinity. So this also works for x going to minus infinity as well. All right, so what do I mean? These red arrows up here, these terms that are going to 0, they're also going to go to 0 if x is going to minus infinity. Cool. Let's try that technique again. I've got a second example, second rational function. I've got a graph of it drawn over here. So again, using the graph, you can look at it and say what the horizontal asymptote is. The horizontal asymptote of this, I'm going to just abbreviate that HA. It's got the equation y equals, well, what is the y value of that red line that the blue curve is approaching? It looks like it's y equal to 0. So this limit that we should compute, we should get 0. Let's see how the algebraic computation goes. In this case, the highest power of x, it's also x squared. That's not always going to be the case, but it is in my examples so far. But it's only in the denominator, right? There's no x squared term in the numerator, but that's okay. I still begin by dividing everything by that highest power of x. So I'm going to try to squeeze this in here so I have some room to work below. But I'm going to take those 4 terms one at a time and divide them all by x squared. So I'm dividing x by x squared. I'm going to divide 3 by x squared. I'm leaving the same algebraic operations, plus, minus. I'm just dividing everything by the highest power of x. All right. And now I'm going to use some rules of exponents to simplify that. I still have to write this limit because I haven't taken it yet, but x over x squared is 1 over x. 3 over x squared is already simplified. These are all just rules of exponents. X squared over x squared is 1. 1 over x squared is simplified. And then we use the theorem. Anything that has an x left in the denominator, there'll never be x's in the numerator because we're dividing by the highest power of x. So the worst case scenario is a term like this where all the x's cancel. But if there's x's left in the denominator, then those terms go to 0 by the theorem. So if we continue this calculation, what are we going to get in this case? If we take the limit now, the numerator is 0 minus 0. The denominator is 1 minus 0. That's 0 over 1. That's, that's 0. All right, so that confirms our observation that we saw from the graph. Cool. Pause the video, think about the algebraic steps, work at your own pace. I'm just going to keep going, trying to keep the video as short as possible. Let's look at another one. This time, another rational function. It's also got highest degree x squared. Shame on me for not making my examples a little bit more, I don't know, non-repetitive, but the highest power of x is x squared. And we're going to start the same thing. If I want to take the limit, well, here I'm just going to continue this thing. I'm going to divide everything by x squared. So x squared over x squared, 3 over x squared. Downstairs, I've got x over x squared, and then I've got a 1 over x squared. All right, and I'm just going to write another equal sign, simplify that before we write the limit notation. So this is 1, take away 3 over x squared was already simplified, 1 over x, 1 over x squared. All right, so if we want to take the limit as x goes to plus or minus infinity of this thing, then of f of x, then we're taking the limit as x goes to infinity of this expression, 1 minus 3 over x squared, 1 over x squared, and using our theorem, any term with x's in the denominator are going to go to 0. So this time, the numerator of this fraction is approaching 1, the denominator is approaching 0. So you remember from our work back in previous sections in chapter 2 that such a limit doesn't exist. When the denominator of a fraction approaches 0 and its numerator doesn't, that fraction either approaches plus infinity or minus infinity. And you can see that in the graph. There's no horizontal line in this graph. I'm going to just draw one like y equals 20. That function value is approaching. It's eventually going to exceed any value or go below any value as x goes to minus infinity. So this function doesn't have a horizontal asymptote. It was evident in the graph when I first revealed the example, and here the algebra is telling us that. All right. So I want to kind of summarize what we've done in these three examples. I'm going to kind of scroll back here for a second. But in this third example, the highest power of x was in the numerator. So when we divided everything by that highest power of x, the numerator didn't go to 0, but the denominator did. That will always force that limit to not exist. Yeah? So it's not just this example, but in any rational function where the highest power of x is in the numerator, you're never going to have a horizontal asymptote. You're never going to have a limit at infinity. Compare that to example 2. In example 2, the highest power of x was in the denominator. So when we divided everything by the highest power of x, the numerator went to 0, but the denominator didn't. We'll always get 0 in that case. And then finally, in example 1, the highest power of x was in both the numerator and the denominator. So when we divided everything by that highest power, any terms that weren't those leading terms went to 0. And so what did we get left with? We got left with the ratio of the leading terms. It'll always work that way. So I'm going to scroll back down and summarize this. It's just a handwritten, it's not a theorem in your book, but it's a handwritten theorem. If you take any polynomial, a polynomial is just powers of x times numbers, the coefficients, and there always has to be a highest power of x. That's called its leading term. The coefficient of the leading term is never 0. That's why it's the leading term. So here I've just kind of got a general rational function, a polynomial of degree n over a polynomial of degree m. And like in example 1, if n and m are equal, then these leading terms, when you divide everything by the highest power of x, every one of those subsequent terms is going to go to 0, and you're just going to get left with a horizontal asymptote. The limit at infinity is going to be an over bm. So that's just like our example 1. They were both quadratic. Like in example 2, if the degree of the numerator is less than the degree of the denominator, that is, if n is smaller than m, then when you divide everything by the highest power of x, the numerator is going to go to 0, but the denominator is not. So your horizontal asymptote is always going to be 0. That's like in example 2. The last case is the flip side. If n is bigger when you divide everything by the highest power of x, the numerator won't go to 0, but the denominator will. That limit will never exist. You'll never get a horizontal asymptote in that case. That's like example 3. All right. So this is a great theorem for limits at plus or minus infinity, because those things will vanish no matter which way x is going, for rational functions. So this applies to ratios of polynomials. So it's a great theorem, a great result for limits at infinity for rational functions. Basically, you can glance at a rational function, quickly determine where is that leading term? Where is the highest power of x that you see? Is it in the numerator and denominator? Is it in the denominator? Is it in the numerator? The answer to that question dictates what the horizontal asymptote is. Okay, pause the video, take a break, think about this for a second. I'm just going to keep going. I've got some more examples. This video is going to get a little long maybe, but you can keep pausing it and coming back. Here I don't have a rational function. This next example is not a rational function. The denominator of this thing is an exponential function. I don't really have an algebraic technique to show you here. Later on when we talk about L'Hopital's rule, we'll circle back to this and I'll show you an algebraic technique, but we're just going to use the graph. So we're going to use the graph to investigate this limit. And you can pause. Can you say what it is? The limit as x goes to infinity of x over e to the x, looking at that graph, what are the y values on the blue curve approaching as x goes to infinity? It looks like they're approaching 0. We've got a horizontal asymptote as y equals 0. Notice that unlike any of our rational function examples, the limit as x goes to infinity of this same function doesn't exist. So it's not always the case that just because you have a limit in one direction, you have it in the other. It will always be the case for rational functions, but not for arbitrary functions. As x goes to minus infinity, the y coordinates on this graph, x over e to the x, they are just becoming more and more negative. So if you want, you could be more precise here. You could write, well, this limit is negative infinity. That's just sort of a more precise way of saying it doesn't exist. I'm going to state without proof here a fact that if you take the limit as x goes to infinity of any polynomial function over e to the x, you're going to get 0. What does that mean? Ratios are going to 0 when the denominators are big and the numerators aren't. So one way to interpret what this fact is that exponential functions grow faster than polynomial functions. E to the x grows faster than p of x. Grows faster in the sense that as x goes to infinity, both of these quantities, p of x and e to the x, are becoming infinite, but e to the x is so much bigger that their ratio is going to approach 0. So I'm not proving that right now. I'll prove it later on when we get L'Hopital's rule, but it is a fact that I want you to put in your back pocket, that if you're looking at ratios of polynomials to exponential functions, the exponential functions will be so big that the ratios tend to 0 as x goes to infinity. Let's look at another one. It's kind of a different nature. It doesn't have an exponential function in it. It's got an oscillating function. Again, I hope looking at this picture, and you can always use a picture. I can't emphasize this enough, that these algebraic techniques are important, but you're never in a case where you can't tell me what this limit is. Looking at the picture, can you do it in this pre-calculus language? What's the horizontal asymptote of that function? That red line looks like it's at level 0. That limit looks like it's equal to 0 from the graph. This is kind of a cool example because notice that this function is crossing its horizontal asymptote. Sometimes people think that that's not possible, but this one is. In fact, it'll cross that horizontal asymptote infinitely often. Yeah, this is kind of a cool. I haven't spoken about applications of limits at infinity, but they're usually when you're interested in the kind of long run behavior of your function. So maybe this is some, I don't know, in physics, maybe this is a graph of some spring system, and the y coordinate is its distance out of equilibrium. So you've stretched the spring 1 unit out of equilibrium and you let it go, and then the spring goes below equilibrium, it compresses, but then it comes back out and it goes back out. Maybe it's a shock absorber in your car or something like that. So this limit at infinity is its long run behavior. What's that system going to do in the long run? As x goes to infinity, it's going to return to equilibrium, if you like that example. Okay, so how could we compute something like this algebraically? Well, I want to circle back and kind of remind you about one of our tools called the squeeze theorem. So one way to see this would be to remember that the sign of x is never more than 1 or less than -1. So if you divide everything by x, which is going to infinity, so it's positive, it's not going to change any of these inequalities, then we get that. And then by our work above, I'm just going to kind of do this notationally, -1 over x and 1 over x simultaneous are both are going to go to 0 as x goes to infinity. Yeah, as x goes to infinity, 1 over x, and that's by theorem 5 above. -1 over x and 1 over x go to 0. So this thing, the limit as x goes to infinity of sine of x over x has to be 0 by the squeeze theorem. It's trapped in between. The squeeze theorem that we stated before wasn't valid was stated only for limits at a finite number, but it's valid for limits at infinity as well. So there you go. There's an application of the squeeze theorem, that wave, and in this case, it goes to the same is true for negative infinity. You can see in the picture that this horizontal asymptote is on both sides. Cool. Okay, pause that, soak it in. Let me continue here. Here's kind of an interesting example. This function has limits at negative infinity and infinity. You can see it in the graph. It's not clear what those y values are of those red lines, but you can see that it has 2 horizontal asymptotes. They're not the same. Yeah. So not only can a function have an asymptote in one direction and not the other, it can have it in both directions, but they don't actually have to be the same. So I want to investigate this limit with you guys. I want to know, well, like, what are these y values? Oops, sorry about that. What are those y values? They look like there's some numbers between, the upper one is between 0 and 1, the lower one's between -1 and 0. I want to know what they are. So we're going to kind of proceed the same way we do with rational functions, the highest power of x, but you got to be a little bit careful. You're probably looking right there, which is good. That is the highest power of x, but the highest power of x in this function is not really 2, because that x squared is under a square root. And when you take the square root of a square, you have the first power. So this thing is really first degree over first degree. It's not a rational function, but it's going to behave more like the function where that highest power of x is 1 in the numerator. So let me give you sort of an example of how you can manipulate this thing algebraically. So let me try to write neatly so I don't run out of room here. It's going to slow me down a little bit. Under that square root, I'm going to factor out an x squared. So I'm going to have the quantity 2 plus 1 over x squared. Not doing anything in the denominator here for a moment. It's 3x minus 5. Okay? And now I'm going to take the square root of the product by taking the square root of each term. When you take the square root of one thing times another, you can take the square root of the first thing times the square root of the second thing. Was that too obnoxious? Square root of the first thing times the square root of the second thing is what I'm going to write over here. But the square root of x squared, the square root of x squared is the absolute value of x. So I'm going to get the absolute value of x plus square root of 2 plus 1 over x squared. Divide that by 3x minus 5. Okay, now my x is going to infinity. My x is going to infinity. So the absolute value of x is just x. X will eventually be positive. So I'm going to write this as the limit as x goes to infinity of just x times that square root term over 3x minus 5, right? Why is that true? Because the absolute value of x is x if x is positive, and our x is positive. It's going to infinity. And now I'm going to divide everything, numerator and denominator, by the highest power of x. Be careful, this is a product there. It's not a sum. So when I divide everything by the highest power of x, what am I going to do? I'm going to write the limit as x goes to infinity, x over x times that square root. I don't have to divide everything by the x inside the square root because it's a factor, not a term. Down here, I divide 3x by x, and I divide 5 by x. All right, giving myself some room to work here. Let's continue. What do we got? The limit as x goes to infinity of, well, just 1 times the square root of 2 plus 1 over x squared. And in the denominator, 3x over x is 3. 5 over x is already simplified. And now using limits and continuity, right? I can take the limit of a square root by taking the limit under it, or I can take it before it. So using all of those limit properties, I'm just going to kind of symbolically write that 1 over x squared is going to go to 0. 5 over x is going to go to 0. And then using limit properties and the continuity of square root, what do we get? In the numerator, we get the square root of 2. And in the denominator, we get a 3. All right. So we just learned that y value. I'm going to scroll back up so I can label it. That is the horizontal asymptote as x goes to positive infinity. That y value is the square root of 2 over 3. You can get out a calculator and get a decimal value for that. Right? So its exact value is the square root of 2 over 3. So, well, what about this negative one? It seems like all the algebra that we did is valid. So what's going on with this thing? Why did it end up having a negative horizontal asymptote? It's kind of a subtle thing. That negative happened, let me just kind of do it with a highlighter, right here, right? Because if we switch x going to minus infinity, then x is not a positive number, x is a negative number. And if x is a negative number, then the limit, or excuse me, the absolute value of x is not equal to x, it's equal to its opposite, right? So I think I'm just going to clip this. You won't see this for a second, but if I make another copy of that thing, oops, I'm not happy with that. I'm just going to drag this down here and sort of modify what's happening if we take the limit. Let me move this over here and write the limit as x goes to negative infinity of our function. I'm just going to call it f of x, and then let me clean this up a little bit. So I'm going to negative infinity now. And the crucial step is what we just said. When we erase the absolute values, if you have a number that's less than 0, which our x will be if it's going to negative infinity, then its absolute value is its opposite. So when we erase those absolute value signs, we have to replace x with negative x. All right, and then the rest of the manipulation would be the same. I won't write it all again, but when you do this cancellation in the numerator, you won't be left with just that square root. You'll be left with its opposite. So you'll end up getting -2 over the square root of 3 for the limit. All right. So there's just a little bit of subtlety about what can happen when you have powers under a root and the absolute value function gets introduced. So let me scroll back up one more time. Sorry, this is a little messy, but I'm doing my best. So there's your lower absolute value, or horizontal asymptote. Sorry, my tongue is all over the place this morning. The lower horizontal asymptote for that function is y equals negative square root of 2 over 3. Cool. Okay, well, this video has been long. Let me just end with one more example. This is just sort of a fact that I want you to know. That the inverse tangent function, maybe you can recognize its graph. It's the reflection of the tangent function between -π/2 and π/2. And so its horizontal asymptotes are those values. The inverse tangent function approaches π/2 as x goes to positive infinity and approaches -π/2 as x goes to -infinity. Right, so those are its horizontal asymptotes. This red line up here has value y equals π/2. It's a little bit more than 1.5. The horizontal line down in the bottom here has equation y equals -π/2. So that's just kind of a fact that I want you to know about the inverse tangent function. It's a handy fact. Okay, so I hope those computations were valuable. I hope this video wasn't too long. You paused it along the way, and thanks for listening.